What's up, math scholars? It's Friday, so who's excited for the weekend full of snow and cold weather? Yeah! Skiing, snowboarding. Okay, so we are doing 3.1 day 1. Good luck to the cross-country people. I feel like a couple of you might be watching the video because you went down to state. Stay warm, wear your snow pants. Unless you're running. Good luck, Lauren. All right. Okay, so these are the properties of exponents. We've learned all of these. You don't need to write this down. It's just a reminder. If the bases are separate, you add the exponents. If they have a little parenthesis, you multiply the exponents. If there's a group, you distribute the m to everybody. If there's a negative, you flip and make it positive. If there's a fraction, you do bigger minus smaller, put the answer where the bigger lived. And then if you have an exponent with a fraction, it would distribute with that. So we've learned all this. In fact, I think you taped it in your notebook last chapter. Remember that? All right, so we're just going to do some properties with exponents. This time, our exponents are fractions. That's what makes it different this chapter. So we've got 7 to the 1/4, and we're going to add it to 7 to the 1/2. Or I didn't say that. I kind of messed up but gave it away. What we're going to end up doing is adding the 1/4 plus the 1/2. So guess what needs to happen? Common denominators. When's the last time you thought about common denominators? One person told me middle school. It's time, if you're a junior or sophomore, maybe even a freshman, it's time to think about common denominators. It's been a while. So you can keep the 1/4, but you need to make this denominator 4. So 1/2 would actually be 2/4 if I would make a common denominator. Does that make sense? We can go ahead and add it up. That'd be 7 to the 3/4. Alrighty, we got our next one. What do you guys think we should start doing first on this problem? How should we start this one out? Casey?
We should add the fraction exponent.
That's a good idea, but the 6 and the 4 are different bases. We can't use that trick. What we're going to do is just distribute this 2 within. Now when you distribute the 2 to here, the 1/2 and the 2 multiply together. So what is 1/2 times 2? 1. And then the 1/3 will multiply by 2. And 1/3 times 2 is 2/3. At this point, 6 and 4 are not like bases. There's really nothing more to do. The book just kind of stopped here. You don't have to have that little 1. It can be invisible. Okay, part C. Here's our next one. So when I saw this problem, the negative really caught my eye, and I was like, let's flip and make it positive. But then I said, okay, maybe we'll wait and distribute it in. So I actually just chose to distribute it in first. What is 5 times negative 1/5? 5 times negative 1/5 would be a negative 1. And then 5 times negative 1/5 again would be a negative 1 again. So that just kind of cleaned it up a little bit, I thought. And now we can worry about flipping. Does the 4 need to flip to the denominator? Yes, because the 4 has a negative exponent. So we're going to flip it and make it positive. Does the 3 have to flip to the denominator? Yep, we can flip it and make the exponent a positive. So our final answer on this one is just 1/12. All right. Part D. So I think the first thing I'll tell you about is there is technically an invisible 1 right about here. Do you know what we should do? Good. Bigger minus smaller. Put your answer where the bigger live. Now, who's bigger, 1 or 1/3? The 1. So you're going to do 1 minus 1/3. Put that in the exponent position of the 5 and put it in the numerator. So what is 1 minus 1/3? It's 2/3. It's technically 3/3 minus 1/3, but yeah, it's 2/3. So the final answer is 5 to the 2/3 power, and it's up in the numerator position because that's where the biggest exponent originally had lived. All right. This is the last one we're going to do with the exponent rules, and then we'll move on to simplifying radicals. All right. How do you think you should start this? What's catching your eyeball? Well, I chose to distribute the 2 in first. I don't know if that's the right answer or the wrong answer, but it works. So we're going to distribute the 2 to here. We're going to do 1/3 times 2. And 1/3 times 2 is 2/3. Then we're going to do 1/3 times 2, and 1/3 times 2 is 2/3 again. Now at that point I was like, 42 and 6, they have different bases. There's maybe nothing more we can do. But then, got an idea. We're actually going to kind of undistribute the 2/3. I'm going to write it like this and see if you can see what I did. 42 over 6 to the 2/3 power. So I kind of took the 2/3 power out front and undistributed it. You see how that works? That little magic trick right there. And that allows me to do 42 divided by 6. So the final answer is 7 to 2/3. It's pretty cool how that one works. It's a little bit tricky doing that strategy. All right, well, we are moving on to simplifying radicals. These are 2 properties of radicals you've seen before. You don't need to write them down. Basically, if you have 2 numbers under a radical, you can split them apart, and you can go backwards with that property as well. And then if they're underneath a fraction, you can break them apart, you can go backwards with that property. The key is they have to match. So you can't like take something that's a square root and then multiply it by something that's a cube root and try to put them underneath one big deal together. You just can't do that. These 2 have to match. They either both need to be cube roots or they both have to be square roots. So in this case, if it was the cube root of 4 times the cube root of 5, I could make it the cube root of 20. Does that make sense? But the type of radical has to match. All right, it says use the properties of radicals to simplify this expression. So first of all, do they both match? Is this a cube root and is this a cube root? Do my roots match? Sure thing. We can put them underneath one giant cube root together. 12 times 18. Can you guys go ahead and multiply 12 times 18 for me? Now we're not in my classroom where I would say to you guys, is 216 up on the perfect cube list? Does anybody remember? It is, it is. So go ahead and type it in. What's a cube root of 216? It's a perfect cube. It's 6. Now is it plus or minus 6 or just 6? That's yesterday's lesson. It's just 6, and it's just one single answer because this is an odd radical. It's when you do even radicals, then you get your 2 solutions. Okay. Let's try this one.
20 cubed.
Oh, sorry, yep.
I think that's just the picture.
Could be, yeah, my picture's low, pixelated. Okay, so in this case, we have the 4th root of 80, we have the 4th root of 5. They are both 4th roots. So I'm going to put them underneath the big, giant 4th root together. Can you guys calculate out 80 divided by 5 for me? 16. Now, I actually added on a perfect 4th root list on my board today. But guess what? 16 is a perfect 4th root. What is it going to be? You can type it in if you need to. You do it in your head.
Plus or minus 2.
Good. And Liberty, remember we need that plus or minus. Why do we need that plus or minus, Liberty?
Because it's a positive.
It's because it's an even.
I meant that's right.
Yeah, you're even rooting a positive number. Let's pause our life real quick here to make a perfect 4th root list. So in my classroom, I've got a perfect square list, perfect cube list. Our perfect 4th list is going to be 1 to the 4th power, which is 1. 2 to the 4th power, which is 16. 3 to the 4th power is 81. 4 to the 4th power, 256. 5 to the 4th power, 625. 6 to the 4th power, 1296. 7 to the 4th power, 2401. That's probably enough. It gets a little confusing when some of these appear on the perfect fourth list and the perfect square list, and maybe some even appear on the perfect cube list. It just depends. Like, most of these are going to be perfect squares as well because they're perfect fourths, so it's kind of unique. Actually, they are all going to be perfect squares. All right, while we're doing this, let's make ourselves our perfect fifth list. Why not? While we're paused. So this is the people who are perfect fifth roots. Perfect fifth roots list. 1 to the 5th would be 1. These numbers get big quick. 2 to the 5th, 32. 3 to the 5th, 243. 4 to the 5th, 1024. 5 to the 5th, 3125. 6 to the 5th, 7776. It's probably big enough. I'm not going to give you numbers any bigger than that. All right, did you make your lists? We're going to need these lists in a few minutes. Oh. Suddenly they decided they should write the list down. Yeah, we're going to need these lists in a couple minutes. All right, and we will end the day with breaking some radicals down. Now, we've learned this, breaking factors out of jail, but when you get into third roots and fourth roots and fifth roots, it gets really messy, and you have these huge factor trees. So I'm going to teach you a different method that still will work. I mean, the jail method still works, but this method is great too. And this method is always breaking it down so that one of them is a perfect radical. So this is a square root. I'm going to break the 50 down into 2 square roots such that one of them is a perfect square. And you want to pick the largest perfect square you can. So Dylan's figured it out. Yeah, 25 is the largest perfect square you can possibly break 50 into. And then we all know that the square root of 25 is 5. And then this square root of 2 just stays because it's not a perfect square. And that is how the answer would be. You get the same exact thing had you done it with the breaking guys from jail and circling the groups and bringing them out. This is going to be kind of a better method for when we get to this larger roots. No, we are not nowhere near done because we haven't broken any cube roots down, fourth roots, or fifth roots. Let's do one more square root one since we're using kind of a new method. So we're going to break the 72 down so that one of these two is a perfect square root. We want the largest number on the square root list as possible. So you remember your square root list, right?
Yeah.
1, 4, 9, 6, 36. Good. So she thought that if she did 36 and 2, it'd be best. I had somebody last year, they did 9 and 8. I'm like, that's a great idea. 9 is a perfect square. But that wasn't going to get us broken down quite enough. So 36 and 2 is the best choice. The square root of 36 is 6, and then you have the square root of 2 here. And you don't need to put the plus minus on these problems. I looked in the book, and the book does not. So it's more like when you're solving for a variable, you put the plus minus. All right, you want to try a perfect cube problem? Oh, yeah. All right, we're going to attempt to break down a perfect cube problem and simplify it down. So our goal here is to break it into 2 factors such that one of those factors is on our perfect cube list. And we want the largest one we could find on the perfect cube list. Let me get that perfect cube list up on the board right here, since it's at my classroom back down the hallway. 1 to the 3rd is 1. 2 to the 3rd is 8. 3 to the 3rd, 27. 4 to the 3rd, 64. 5 to the 3rd, 125. 6 to the 3rd, 216. And that's probably big enough because we're already over 135. All right. So if I look on this list, what's the largest number on the list that will break is a factor of 135? I heard Caitlin saying 27. So 135 is 27 times what? Very good. The cube root of 27 is a perfect cube. The solution to that is 3. And then this third root of 5 just stays there. Don't remember this little baby 3, or don't forget this little baby 3 in your final answer. Sometimes people forget it, and that changes what your answer is. If you forget it, it's a square root that needs to be there to denote that this is a cube root. Questions on how that one works? Our first cube root ever. Let's try 72. We want to break 72 down so that one of the factors is on my perfect cube list. So is 64 a factor? Is 27 a factor? Is 8 a factor? 8? All right. So we're going to go with 8 times 9. 9 is not a perfect cube. 8 is. What's the cube root of 8? 2. So my final answer is 2 times the cube root of 9. I really have 2 more. I know it's Friday and you want to take a nap. Plus, I'm really hot. Are you guys hot? Are you guys hot in here? Yeah, I'm really hot. I'm cold. All right, we're going to do a 4th root problem. Woo! Good thing we have that 4th root list up on the board up there. So we want to break 80 down, and we want to break it down with the largest number on our perfect 4th root as possible. So obviously 81 won't work. Let's see if 16 will work. There's 80 divisible by 16.
Yes.
16.
So it's 16 times what? 5. Okay. Oops, I wrote 5 in the wrong spot. And then the 4th root of 16 equals 2. So it's 2 times the 4th root of 5. All right, 5th root of 729. What is the largest number on my 5th root list that would work? Will 243 work? Will 32 work? Let's see. Obviously, we don't want to try 1024. It's just too big.
Two, 43, and 3.
243 and 3. Thank you. And then what is the 5th root of 243? 3. So our final answer is 3 times the 5th root of 3. All right. Hopefully you had a fun field trip today, students. Magical school bus. No, but have a happy weekend. Here's the homework. Jot it down. And thanks for watching the video.